series. Today we're very fortunate to have one of our former fellows, Simson Garfinkel, back here to tell us about what he's working on these days. Simson is an extremely broad and well-known figure in privacy and security, broad both in the kind of work he does and in his background. He has degrees in political science, chemistry, journalism, science, technology, and society, and computer science. After his computer science PhD at MIT, he came here as part of our first cohort of fellows, and having as dynamic and visible fellows in our first group as like Simson really was, I think, what got Circus off to a very strong start. Simpson, I also mentioned his activities are very broad, so in addition to the computer science work he does in privacy and security, he is also well known as a journalist, and he's also started several companies, and he's a faculty member at the Naval Postgraduate School. So Simpson always does extremely interesting work, and I'm sure the work he'll be telling us about today is no exception. So glad to have you here, Simpson.
Thank you. So we have about an hour, and then there's time for questions. I have 87 slides, which is probably too many, but the slides are available on my website, so I'll be reading parts of them, but other parts will just go very quickly. I'm with the Naval Postgraduate School, and for those of you who don't know, it's a university operated by the Department of Defense in Monterey, California. We have about 1,500 students. Most of them are active duty U.S. military, but we also have civilians. We have master's programs and PhD programs, but most of our schools are master's students. Most of our students are masters. and this talk is about computer forensics, and specifically about computer forensics of information on stored media. So what you might say data at rest. We're not going to be talking about network forensics. We're not going to be talking about malware analysis. But the DoD, law enforcement, there's a huge amount of stored data that is being encountered in the course of law. And even if you do e-discovery, law firms are getting lots and lots of hard drives, and they have to analyze them. And the techniques that we're talking about for analyzing hard drives also work for analyzing cell phones with some caveats. But it's a very, very hard problem. And the reason the problem is hard is because of the quality of the data and the quantity of the data. Now, when you are looking at your computer, you see information from address books, emails, documents, photos. But when you're analyzing somebody else's computer, you have no idea what the information is. It may have all that information. There may be additional information in document formats that you're not familiar with. And you have to look everywhere because you're looking for information that might be useful for a conviction, might be useful for proving somebody's innocence, or might be useful for an intelligence operation. Now, when you're looking at your own computer, primarily you're interested in the intact files. But when we're looking at other people's computers, we're also interested in what's called the residual data, stuff that's not in allocated files. And this might be slack space within a file. Microsoft Word has this privacy problem, and sometimes it leaves deleted sentences in document files. Well, that might be very important in an investigation. But we're also looking for information that might be left in the virtual memory swap files or in hibernation files. Now, here's a particular problem. You might have a JPEG which has been deleted, and then the first half of the JPEG has been overwritten with other information. Well, that second half of the image might be very, very important. It has information that the owner of the computer doesn't know is there anymore. But that might be the information that makes your case. So until very recently, we had no tools for being able to display the second half of a JPEG when the first half was missing, because that's compressed data. But because of research in this area, Nasser Merman's research at NYU, we now have the ability to reconstruct the second half of a JPEG, even if the first half is missing. So residual information is very important because it can reveal facts, motives, state of mind, and associations that the subject tried to hide from other people. And unfortunately, computer science lacks techniques for resolving incomplete data structures. Very little work has been done on data recovery when the data is partially corrupted. Now, the other thing that makes computer forensics really hard is the quantity of information we have. You have a computer at home. I have a computer at home, this computer. You might have a terabyte hard drive, and you've spent years assembling the information. But an analyst might have to have hours or maybe a week or two to pull the information off that and make sense of that. And it's very hard to make sense of other people's filing systems. So the other problem that we have is this one of resource advantage. In police departments, they typically have a single computer to perform forensic analysis. So we are analyzing the bad guys' top-of-the-line computer systems with our top-of-the-line computer systems. And they've spent years assembling the data, and we have weeks or hours to pull the data out. Now, this isn't the situation with national organizations. National organizations have large-scale server farms to do computer forensics, but they're also collecting a huge amount of information. And so there's no real resource advantage. The only advantage that a large-scale organization has is the quantity of data. Today, that's a problem. But I'm looking at, it's a problem today because there's so much information. We have human analysts, and they don't know where to start. They look at one case, and it's it's hard to correlate data between cases. One of the areas of my research has been specifically looking at ways of leveraging large data sets so you can use that large data to your advantage. Now, a complicating factor in doing computer forensics research is that the same technology is used for multiple purposes. There are different kinds of examinations. For most of the past 20 years, the main use of computer forensics has been looking for evidence of a crime to support a conviction. And the most common case is looking for child pornography, although here I have financial records just to make the slide nicer. And in many cases, if you find that kind of evidence, you can put somebody in prison simply for possession. But increasingly, we're interested in using computer forensics to support an investigation. So if we can find a cache of like Google Map information with paths shown, that reveals something about a case. If you find search terms that a person was typing into the computer, that can reveal intent. There are several cases where a person murdered, you had a case here in Massachusetts recently where a person murdered their wife and daughter. And the prosecution used the fact that the person had done searches for information on how to murder people as proving intent. The third reason that people are doing computer analysis now is to look at artifacts of intrusions. And this is a cybersecurity situation where you might be looking for vulnerabilities and exploits, but you also might be looking for evidence of how they got in, and you might be looking for data that's inconsistent, people trying to hide their tracks and not doing it perfectly. So ideally, we could have some software that examines all the data structures on the computer and looks for things that are inconsistent with the application suite that's running on the operating system. But that software doesn't exist. So this talk is going to introduce digital forensics a bit for people who are not familiar with it. I'm going to talk about some of my work on creating a corpus of digital forensics information and why that's important. I'm going to talk about this data mining machine learning project we did with multi-user carved data ascription problem, and you'll understand that when we're done. And then I'm also going to talk about this new technique called random sampling. Random sampling is not new, but using computer forensics is new. So computer forensics, digital forensics, it's about extraction and analysis. So data extraction is the first part. Here you have a hard drive, and this is a device called a write blocker. It allows data to be read but not to be written. The data gets stored on a server, and the original evidence gets put in a data locker somewhere, evidence locker somewhere. And we have special machines for extracting data from cell phones. But cell phones are a real problem because there's a real lack of standard connectors, and it's difficult to work with them, and they don't really have provisions in them for getting the data out in a principled manner. And once the data is removed, we use computer forensic tools to examine the data. This is a very popular tool. It's called Encase. And what it does is it lets you see all the files, the deleted files. It lets you see all the email messages, the deleted email messages. And it allows the examiner to do string search. And based on that, the examiner basically drives the computer around, looks through the file system, tries to assemble what had happened. And it's a very slow process. But it's worked pretty well for the past decade. And so I say the past decade was the golden age of digital forensics because most of the bad guys were using Windows XP, Most of the investigators were looking for Microsoft Office files and JPEGs. Most examinations dealt with a single computer, usually belonging to a single bad guy. And most computers were using standard interfaces, IDE and USB. And so we got some standard tools. A tool called Encase, a tool called FTK. There's a certain amount of open source software. And there's this tool made by Oracle called Outside In, which basically understands 350 different file formats and will extract the text from them. And it's a solved problem, except it's not. So today we're in a digital forensics crisis. And the problem is we have a lot of tools that were designed to take data and present it in court. And they don't scale to having hundreds or thousands or tens of thousands of hard drives. And in looking at this, at why we're in a forensics crisis right now, I've come up with 5 fundamental problems that we're facing. The first one is this increased cost of extraction and analysis. Consumers can buy 2 terabyte hard drives for $100. Cases now have multiple devices. Single person might have 2 desktops, 6 phones, 4 iPods, and they all have to be analyzed by law enforcement because you don't want to be in a situation where sensitive information was left behind. There's a proliferation of operating systems and file formats, especially in the cell phones. And here's some case data from the FBI. The number of service requests from FY08 to FY09 went up by 11%, but the amount of terabytes they processed went up by 32%. So we're seeing more and more data associated with every case. The second problem we're dealing with is mobile phones. They're very hard to examine. Most of my research is not on mobile phones, but I want you to know that's a problem. The third problem we're dealing with is encryption and cloud computing. Now, both of these have the effects of taking data away from the examiner. Encryption locks it away in a cryptographic vault, and cloud computing locks it away on some other system. But especially with cloud computing and a little bit with encryption, there may be residual data left on the devices that's available for us to analyze. It just won't be in files. A fourth problem is RAM forensics. It's not an area where I've been doing research. This is in its infancy. There's a lot of opportunities for analyzing artifacts that are left in RAM or what's in the GPU, what's in the Ethernet controller. There's lots of places for malware to hide and lots of opportunities for adversaries to reprogram our BIOSes. It's an important area. It's not where I'm working. And the fifth is this time problem. Most of the tools that we're working with were designed to perform a complete analysis, but increasingly we're racing the clock. Police departments are actually running out of time because of statute of limitations. But on the battlefield and intelligence and cyberspace, we need to do turnarounds in days or even hours once information is collected. So my research area, I've been focusing on 3 research areas. The first one has been data collection and manufacturing. We've been trying to create very large-scale data sets we've been trying to create data sets in the 10 to 20 terabyte range to enable real science on problems at scale. And we've been trying to create smaller data sets under a terabyte for use in education. We've been trying to take the best data mining algorithms that might be applicable to computer forensics and actually get them out there and figure out how we have to modify these algorithms to make them appropriate to the forensics problems that we have. And I've been trying to work away from the file level. So over the past 20 years, there's been a lot of interest in working with files. I'm trying to work below files with data fragments that might be left, and also thinking about how to assemble collections of files and artifacts into higher conceptual structures. And there's a heavy emphasis on building tools and actually working with practitioners, because that's how we learn about what's actually needed. Yes?
So on the first problem that you mentioned about there being more data,
yes.
Is it that, at first it sounds like more data is only a good thing for an analyst. So is the problem that you just want to take advantage of this additional data and it's difficult to do so with current tools, or that the useful information is somehow harder to find in the larger?
Well, it's both. So if you collect a hard drive from somebody that has 2 terabytes of data, the tools take dozens of hours to process that, maybe 70 hours. So the tools just are running much slower. They don't parallelize. There's some operations where we don't know how to parallelize them. And then most of today's tools follow what I call the search, filter, and report model. They just build a big database, and they let the examiner do searches on that database. And string search becomes less and less valuable when you have a larger and larger corpus of information to search. Now, this was a problem on the World Wide Web back in the 90s. Alta Vista was returning more and more results. Google came up with this idea of doing link analysis and search rank to make search useful again. But we don't have that ability on a hard drive. We don't have the usefulness of links pointing at the useful data, and we also have this problem with residual data. So when people do searches on the larger drive, they get back more and more data. We need some way of winnowing that out. So thank you for the question. So I'm going to talk now about the forensic corpora. So as I said, I didn't say this, but digital forensics today is at a turning point. Yesterday's work was primarily concerned with reverse engineering, cracking file formats, getting information out, and we now have some commercial tools in that area. But moving forward, work is going to be increasingly scientific. It's going to be about evidence reconstruction, looking for information that's inconsistent, clustering, data mining, social network analysis, because we don't have the time to look at all the data. So we need to have the computer find the stuff that is relevant to the case at hand. And if we're going to be using scientific process, if we're going to be using science, we need to engage in this dialogue. We need to be able to have repeatable results. We need to be able to share research information. We need to be able to publish in a way that's useful to support other people in the field. And that doesn't happen today in computer forensics because everybody is working with their own data sets. There is no large publicly available repository of computer disk images other than mine. Most people who are developing tools are developing those tools with their own hard drive, and then they can't publish the actual results of the tools. And so there's been some 10 years of research in a particular area called file format identification, and people published different algorithms and reported how well they did, but all the work was done on different data sets. So there's no way to compare the individual algorithms. So we've discovered that digital forensics education needs corpora too. A lot of people in the field spend their time creating scenarios, disk images, network packets, and the teachers spend so much time working on this that they don't have the time to prepare their courses. Or it just takes a lot of time, or the scenarios are not realistic. Now, some teachers get hard drives from eBay the way I used to, and the problem is that you don't actually know what's on the disk when you give it to the students. You don't want to give the students pornography because that would be illegal if they're under 21. Some teachers have their students examine each other's machines, and that turns out to be a bad idea because the machines might have confidential information on it. Some teachers have the students examine their own machines, but then that's the problem of how do you report the information. So what we started doing a few years ago was manufacturing information that can be freely redistributed. I work for the federal government. One of the insights was there's no copyright problem redistributing information that's made elsewhere by the federal government. So we collected 1 million files from US government web servers, characterized them, and have been freely redistributing them. We will send you out a hard drive with 500 gigabytes of data on it, and people can download it from our server. And we're now beginning to see research papers using this corpus. Now, the big advantage over YouTube is persistence and copyright. I know people have been doing research on YouTube videos, and then the video disappears. So somebody I know was seeing the YouTube videos disappear at the rate of 2.5% a month. They're taken down. They just become, they disappear. So we don't have a complete collection, but we have a widely varied collection. It turns out we don't have any multimedia. We don't have any video, but we're making some video. We have some really weird XML files. We have some log files, and the value of this data set is that it's very heterogeneous. We've been creating test and realistic data sets. So we actually have an NSF grant to build forensic scenarios and distribute them, and this is about 1 terabyte. And we have a university harassment scenario, which involves packets, and we have a company theft and child pornography scenario where we have to create simulant child pornography, so we don't want to distribute real child pornography. So we have cat photographs, and we have the Monterey Kitty collection. And then we also acquire real data. This is actually a photo from my old lab here at Harvard, just next room over. We call this the real data corpus. It's up to about 20 terabytes. Disks, camera cards, cell phones, imaged, and distributed. And this allows people to either work with many different kinds of disk images or to begin looking at clustering algorithms or algorithms that make use of large amounts of data. So, and it turns out that it's hard to assemble a 20 terabyte corpus. It's hard because the data is so varied. And it's hard to work with the files. And it's hard because you need to have principled ways for moving the data around and for doing the analysis on all the drives at the same time. So I've been making a lot of use of the NPS supercomputer. We have an 1100 core cluster and 115 terabytes of online storage. So I'm actually one of the biggest users of the supercomputer. And it's been fun. So, yes, sorry.
Are you trying to include deleted data or just actual files?
Well, what we actually do is we copy all the blocks off the hard drive.
Oh, so it's an image that you do have.
Oh, yeah. So we don't do XCopy. We do DD.
Right, but you're creating
Yeah.
An image that has
Mhm.
deleted blocks.
And it turns out that working with this data so this data is all purchased on the secondary market. Our data is actually harder to work with than the data in law enforcement collections. Because most of the time law enforcement gets a hard drive, the suspect was using the hard drive. Whereas most of the time we get the hard drive, it was sold on the secondary market because it was broken and somebody formatted it. So only about a third of our hard drives have intact file systems. But we have a lot of variety. And so some of the hard drives were used by the same organization, and we can actually automatically find the hard drives used by the same organization with a technique called cross-drive analysis. We can automatically find the hard drives used by multiple users. And in this next part, this is about automated description of multi-user data, and it goes directly to your question. You have a hard drive where some of the files belong to one user, and some of the files belong to another user, and some of the files are deleted, and you can't figure out what the original file name was. And so we'd like to be able to understand who was responsible for those files, one user or the other user. Now, it turns out that a typical hard drive now that you pick up might have 1 million files on it. And we can clearly attribute some of those files to one user and some to the other user using file system metadata. So it might just be, if it's a Windows machine that's stored in documents and settings, username. Or if it's a Unix box, it might be that the files are owned by one user or by another user. But there are files that you find that don't have any old directory entries pointing to them. They're recovered with a technique called file carving, where the disk is examined for like the header and the footer of a JPEG, and then it's validated, and it turns out that there's a JPEG there. There was one case that I was involved with where the carved data was child pornography, and it was on a computer in a classroom, and there were 2 different teachers that had access to that computer. And the school wanted some sort of proof that that file was put there by one teacher and not by the other teacher. But it was carved data, and at the time, there's no way to automatically attribute or ascribe that to one user or to the other user. Now, there's been a lot of work done in machine learning on authorship analysis using content, like looking at the reading levels or looking for characteristic errors. And that's fairly understood how to do that. We can show who wrote Shakespeare's plays. But there's been very little work done in the academic press on using metadata or content to ascribe ownership or agency. Who was responsible for putting it there? Pretty much the best trick we have is some cameras put the serial number in the JPEG EXIF. And so if you look at all the files that are on the disk and you see that one person was responsible for one serial number and the other person was responsible with the other serial number, then you can look at the serial number of the disk image that you have. And we have this little animation here that talks about that. So it may be that you discover that one user, Magenta, made all the JPEGs and the docs, and another user made all the Excel spreadsheets, and the carved data is a JPEG, so it's probably the first user. And it may be some Microsoft formats store the time that they were printed in the metadata of the file. So if Magenta is always printing at 9 and 10 in the morning, and yellow is printing in the evening, and the file you find was printed in the evening, then it's probably yellow. And it may be, it turns out we've discovered that the operating systems tend to cluster where the files are based on other usage patterns. So if all of Magenta's files are around sectors 10 and 20, and all of yellow's files are in the hundreds, and the file you find is in the hundreds, then it's probably yellow. Now, There are some examiners that actually do this, but the problem is they don't have any way for gauging how accurate the technique is. They basically find something that correlates and they write up their report. We've come up with a way for doing this automatically using a tool set that I've been spending 5 years developing. So the way the tool set works is we scan the hard drive disk image, and we extract all the files, all the deleted files, and all the metadata. And we use all that, and then for each file, we also extract its metadata. So in a Word file, we might get out its author and its last edit time. In a JPEG, we'd extract the camera serial number. And then we build a classifier using all of the ascribable files as exemplars. So the files that clearly belong to magenta, we say these belong to magenta, and that's ground truth. And files that clearly belong to yellow, we say these belong to yellow. And then we use that classifier to ascribe the carved data. And so the nice thing about this approach is we actually get an error. Estimate. Now, this is pretty simple data mining. You got a lot of exemplars. You know who they are. You do n-fold analysis, n-fold validation. It's a little more complicated. It's very high dimensionality data, and there's a lot of missing values. So we'd like to use the JPEG serial numbers, but we don't have them in the Microsoft Word files. There's some commonalities between most of the files, like where they're stored on the hard drive. We also have a lot of missing values. And there may be multiple regions, because these are machines that may have been used by one person, then the other person, then one person. So the data is all interleaved. And we found that using time analysis worked very well, but the problem is there's lots of different timestamps stored in the data. There's file print times, there's file access times, but the JPEG store when they were shot, and that was shot on a different computer with a different clock. So we found that we could project all the data onto a user activity timeline, a single timeline of dimensional reduction. That helped a lot. Now, the tool that we have, this is sort of like an engineering slide. We can output everything as XML, or we can output everything as ARFF format, which drops into the Weka data mining toolkit. But and then we also have this ability to have plugins. So we have plugins for each different file type. And this is useful because in the field, people can write their own plugins. And the metadata, it's clean engineering. We'll skip that. So we looked at 2 data mining algorithms. The first was a k-nearest neighbor algorithm, which is pretty old, pretty standard. The nice thing about k-nearest neighbor is it's very easy to explain it to a jury. You can say, well, here's the data that we were trying to figure out who was responsible for it. And here was the closest match. And this was at sector 25,000. This was at sector 32,000. The times were far apart, but the file author was very close. And that information just drops right out from the k-nearest neighbor. We also looked at using decision trees with the C4.5 implementation that's built into Weka. And we found that this approach generally provided higher accuracy than k-nearest neighbor, but the problem was the decision trees that it produced, and here's an example of part of one, were a little harder to explain, sometimes much harder to explain. So in practice, in the research paper, we ran the algorithms in parallel. And so we have a decision made by both algorithms. And if they lined up, that was pretty good too. Now, what do we mean by accuracy? Well, there's this concept in law. There's this decision by the Supreme Court, the Daubert decision, where if you're going to bring scientific evidence into court, there needs to be it needs to be peer-reviewed. It needs to be an understood technique. But there also needs to be an accuracy rate or an error rate. And so we say in this case the accuracy is going to be the probability that the classification is correct. We build a different classifier for every drive. So that means on some drives, there's going to be a lot of correlation between different users and their metadata. And on some drives, there isn't. So we compute the accuracy by doing take one out cross-validation. We take out each single exemplar. We rebuild the classifier. We see how good the classifier was at classifying the piece of data that we took out. And this is actually a really good model for what's happening in the case of carved data. The only difference between allocated data that we know who it belongs to and carved data is that the carved data was deleted and then the directory entry was overwritten, but the data element itself was left behind. So take one out validation actually precisely models the process by which the carved data was recovered. Now this does mean that every hard drive is going to have its own accuracy rate, and every carved file is going to end up having its own classifier, and we can optimize by only building the classifier using the relevant dimensions for the piece of carved data that we have. Complex drive with 100,000 exemplars, well, we run it on the cluster and it takes several hours. Now, this is not reasonable for a police department because the police department doesn't have a big cluster, but they can get access to Amazon EC2, and using our calculations, this one with 100,000 runs could be run on EC2 for about $50. So that's not so bad. And we had some other possibilities in the paper of gauging the accuracy, perhaps using tenfold validation. Now, as I mentioned earlier, one of the key insights was to build a user activity timeline. Now, most computer systems, most multi-user computer systems, are being used sequentially by one user, then by the other user. So we can take a lot of the timestamps that we find in these different files and project them onto the same timeline, do dimensional reduction. And so we can take the file timestamps in the file system for the modify and the access and the create times and actually establish ground truth of when the computer was being used by each person. And we can augment that with print times taken out of the Microsoft Word files. Now, EXIFs are problematic. If the EXIF is in there from the camera, then it's not part of the timeline. But if the EXIF timestamp is there because it was edited on the computer with like Adobe Photoshop, then we call it part of the timeline. So we actually need a lot of domain-specific knowledge here to figure out when we use the timestamps and when we don't use those timestamps. And then we have to translate that into a rule that can be put into the automated tool. And likewise with email messages, there's a whole bunch of times in there, and you want some of the timestamps, but not other timestamps. So I have some pretty data. This is one of the realistic drives that we created in the lab. Students were logging in as the Domex1 user and the Domex2 user. And this shows for each of the users how they got classified. And you can see that for the two cases that we really care about, there's a very high classification rate. 95% of the Domex1 get classified as Domex1, and roughly 95% of the Domex2 get classified as Domex2. Now, one way to read this is if you have your carved data and it gets classified as user F, as local service, then it only has an 81% chance of being correct. Now, this is constructed data in the lab, so the question is, well, what does real data look like? Yes? So the first answer is we don't know, but I would hope that if you go into court, you would report the error rate. So one of the problems with computer forensics tools now is that they have an error rate of 0%. The data is either found or it's not found. And there's been a lot of concern about that. Most of the errors we think come from process in the lab, people mixing up one person's data with another person's data. So this research is about 5 or 10 years ahead of the law. The second question is, does machine learning turn up in court? Most computer forensics doesn't turn up in court right now. What happens is it gets shown during pretrial discovery. Usually the prosecution shows the naughty pictures to the attorney for the defense, and the defense pleads out on the case, and it doesn't go to court. So we're years ahead of the courts right now. But we need to establish these techniques in the literature, or else they won't be able to be used in court. So here's some real data. This is a hard drive that was purchased by a contractor working for me in Mexico. It was imaged in Mexico, sent to my machine over the internet. This machine had all the ones that say blinded are actually real people's names. And then these are the leftover Windows services. And you can see that the exciting thing is that the real data, we actually perform better on the real data than we do on the constructed data in the lab. And the reason I think we perform better on the real data than the data in the lab is that we spent weeks building that data set in the lab. But in the field, they probably spent months, if not years. And user M and user G, they spent a lot of time using that machine. So they really invested it with a lot of personal information. And we were able to use those very distinctive personnel usage patterns to pull out the real data. And this is consistently what happened in all the hard drives that we analyzed. The real data classified much better than the data we built in the lab. And that's not usually the case with machine learning, right? Normally, and so this is one of the nice things about the ability to have that large data set. Now, the other thing was we had several thousand disks images. And when we scanned it for multi-user drives, we only found about 15 or so that were multi-user. So it isn't that common. But it is common enough that it has been a problem in at least one case that I'm familiar with. So we've had 2 theses accepted on this, and the journal article is coming out in December. And if you want to, be happy to send you a copy. So I only have 15 minutes before 12:15. I have a really interesting idea, so I'm going to go on to that unless there are any questions about the description. We're right on time. I'm sorry that I'm talking so fast, but it's so exciting. So from our discussions, by now it's clear that there's resident data on a hard drive, there's deleted data on a hard drive, and then there are sectors that have no data. And we'll call those the green sectors. And you can think about the resident data is the data you can see from the root directory, and the deleted data is stuff that you can't get to from the root directory anymore. And then there are these green sectors that just have no data in them. Now, most tools today follow the exact same process for analyzing the hard drive. They walk they find all the file systems, they walk the file system. For every file, they seek to the file, they read the file, they hash the file. Maybe if there's some extra space, they'll carve the space between the allocated files to try to find carvable files. The big problem, number one, I've said, is time. A 1 terabyte drive takes 3.5 hours to read all the data, but it takes 10 to 80 hours to process using this technique. And the second problem is completeness. A lot of the residual data is ignored. In many investigations, the analysts don't even carve because they just don't have the time. So it takes 3.5 hours to read all the data off this hard drive. Well, can we just analyze it in 3.5 hours? What if instead of recovering the files, we just start at the first sector and we go to the last sector? So this is an idea I call stream-based forensics. You just read all the blocks in order, and you try to make the best you can with it. Now, the advantage is you don't really seek the disk. You can read the disk at the maximum transfer rate as long as you have enough cores, and we do. And you get all the data. You get the allocated data, deleted, the file fragments. The disadvantage is if the file is fragmented, you probably won't recover it. Compressed files, if the first part is on the hard drive after the second part, there's pretty much no way you're going to recover that unless you buffer this in RAM somewhere. There are files that have internal fragmentation, like doc files. You won't get those. And you won't get any file names. So I built a tool called Bulk Extractor. It's a high-speed disk scanner. It's written in C. It stripes the disk, so it basically splits the disk into the sectors that go to the first core, sectors that go to the second core, and it reads and it hands them off to different threads. And one of the challenges we have is you have to be able to work with any size of evidence on limited hardware. So you just can't buffer things in RAM. It's got to go directly to disk. The users, when the program crashes, they can't provide the data back, so it's got to have lots of debugging in it because they can email back maybe a few lines, but they can't provide you with their data because it's protected evidence. And as I said, most of the users are analysts and examiners. They're not engineers. So we actually have to give them data in a way that makes sense to them. Now, one of the things that Bulk Extractor can do is it can find all the email addresses. And so it'll make a text file with all the email addresses, the byte offset, and the local context. And this is useful. People like to be able to run grep through the email and see if an email question is there. One of the realizations we had a few years ago while I was here was that if you build a histogram of the email addresses, the most common email address is that of the primary user of the hard drive. And the other email addresses are their primary contacts. So this is from that Domex user's hard drive, and the most common email address is domexuser1@gmail.com. And then these are the fake ones that we made. But it turns out that this email address, the fourth most common, is ips@mail.ips.es. Now that is not an email address of somebody who's a subject in the investigation. That email address is there because it's in an SSL certificate. It's in an SSL certificate. The same with premium server at thought.com. So there are lots of email addresses that are on the hard drive that have nothing to do with your investigation. Now, this program has actually been used in an actual case. This spring in the San Luis Obispo Police Department, the district attorney had a hard drive and had 2 people in custody. They were accused of credit card fraud. And my contact there got the hard drive the night before the hearing to decide whether or not they were going to be given bail or held without bail. So this is not enough time to do a forensic examination. So he ran bulk extractor on it. They found over 10,000 credit card numbers on the hard drive. So most hard drives don't have 10,000 credit card numbers on it. We knew that the defense was going to say that it wasn't their computer and they don't have the knowledge of how to do credit card fraud. Well, we found that the most common email addresses belonged to the primary defendant, and there were a lot of internet search terms asking how to do credit card fraud. Now, these people were from outside the United States. They were a flight risk. And it turned out that the most commonly visited websites were in a foreign country whose primary language was that spoken by the defendants. And this all came out by running bulk extractor and doing that histogram analysis. It shows up email addresses. It actually pulls up all the common internet search terms because they can be pulled out of URLs. And it has a credit card number recognizer in it. And because it shows everything in context, it's very easy for the examiner to go in and see if they're false positives or not. So it actually worked very well for that examiner. But we would like to eliminate the false positives. So one idea was to just scan. So this approach I came up when I was here. I said, well, we have a lot of hard drives. Let's remove the email addresses that we see on other hard drives. And that kind of works. But then you have to set a threshold and so forth. Another approach is to run the bulk extractor on clean installs of hard drive with operating systems and find out all the email addresses that are built into Windows. It turns out that Fedora Core 12 has 20,000 email addresses in it. Because everybody who's contributed to an open source program, their email address is in Fedora Core 12. And the problem with just suppressing them is that this gives any Linux developer a free pass to engage in crimes, and the tool won't report them. So like people I was working with, they started building up this list of these 20,000 email addresses, and I said, no, we can't do that. It's really bad. So, but then I remember that bulk extractor is outputting the context. And it turns out that we don't care about this guy at Nokia, and his email address is in Fedora Core 12, so I'm allowed to use it. Oh, we don't care about his email address when it's in this context of other files, like the local context that we see in Fedora Core 12. We care about it if it's in a different context. So bulk extractor now produces a stop list of the email addresses in question and the context in which they occur. And you can use that context-sensitive stop list as a way of suppressing the email addresses. We do that on the Domex user's hard drive. And the ones that are relevant to the case stay, but all these ones which are associated with SSL certificates go away. So it works really well. And it doesn't work perfectly, but it works pretty well. It works pretty well. So that's 2.5 hours to 3.5 hours to analyze a terabyte hard drive. The question is, can you do it in 5 minutes? So a DARPA program manager asked me this 5 years ago, and I said, no, there's no way you can analyze a hard drive in 5 minutes, because they'll just put the data where you're not looking for it. Like, they won't put it in a file. They'll have a big deleted file, and you won't see it, and they'll overwrite the directory entry. Terabyte hard drive takes 208 minutes to read it all. In 5 minutes, you can read 36 gigabytes. Or you can do 90,000 seeks. That's it. Now, 36 gig is actually a lot of data. It's only 2.4% of the hard drive, but it's a lot of data. And if we're doing statistics, when you have that many things to sample, that's quite a statistically significant sample. Now, we're very good now at predicting the outcome of elections. We do this because there's 100 million likely voters. And the real trick in doing an election is to figure out who are the people who are actually going to vote. We can't just call people randomly. We only want to call the people, we only want to survey the people who are actually going to be voting. But on a hard drive, it's much easier because we know that there are all sectors on the hard drive. So we can get a random sample of the hard drive. The problem here is identifying the sectors when we sample them. Well, one of the things you can't do with sampling, with random sampling, is distinguish between a file that's allocated and a file that's deleted. We just randomly pick a file, and we haven't scanned the disk hierarchy, then we have no way of knowing if that sector that we pick is inside a file or not inside a file, in a deleted file or in an allocated file. So the obvious easy thing to do, the first thing to do, is we can identify if the hard drive has been properly wiped or not. We can see if the hard drive has data. We can randomly sample and see if the sectors that we look at, if they have data in them or not. So if we read 10,000 randomly chosen sectors on a hard drive, and they're really randomly chosen, and they are all blank, then the chances are that the entire hard drive is blank. And I'll show you the math. But if it turns out that there was one sector in that hard drive that wasn't blank, we're not going to find it with random sampling. We're really going to have to read the entire hard drive. So we're only getting statistics of the population as a whole. Now, if half the sectors have data in them, and we randomly sample, then statistics about half the sectors we read should have data in them. If we read 10,000 sectors and they're all blank, but those are the only 10,000 blank sectors on the hard drive, then somebody's hacked our random number generator. They know precisely where we're going to guess. And this is why you have to do random guessing with real random numbers. Otherwise, the adversary can predict where you're going to look and frustrate you. So this is actually an example of what's called the urn problem in statistics. You're pulling beans out of an urn and looking at their colors and using that to infer about the population as a whole. If you read just one sector, so this is the math for assuming that on that terabyte hard drive, there's only 10 megabytes of data. How many sectors do you have to look at before you know that there's 10 megabytes of data? Well, so the question is, well, if you read just one sector, you have a 99.99% chance of missing it. If you read two sectors, you have a 99.98% chance of missing it. Each time we read a sector, we have a really good chance of missing the data. We're multiplying a lot of numbers very close to 1 together. But if you keep multiplying those numbers together, the odds come down. It turns out, here's the equation. If you read 500,000 sectors, your chances of missing it are less than 1%, which means overwhelmingly, if you make 500,000 random picks of sectors on that hard drive, and it has just 10 megabytes of data, you'll find it with probability greater than 99%. So we can tell if that hard drive was properly sanitized in about 5 minutes without scanning the entire hard drive. Well, we can't tell if it's properly sanitized, but we can tell if it has less than 10 megabytes of data on it or not. So what we've been doing is we've been looking at detectors for different kinds of data and using that to leverage this approach of random sampling. So one of the things that we've learned how to do is to distinguish encrypted data from compressed data. So we can take a hard drive in an iPod, which takes a long time to image because Apple bought really slow hard drives, and we can tell you if there's a large encrypted partition on it, because we can distinguish TrueCrypt partition from Apple multimedia. So we can get a statistically significant sample from that iPod in 2 minutes. And we can distinguish the blank data from the image, from the music data, from encrypted data. And the results that we get really approach the correct numbers. Now, the challenge in doing this is to be able to infer the type of a file from reading a fragment from the middle of the file. And it's a problem because files have a lot of internal structure. And so if you're going to try to do this you need to know about all the different kinds of types. So the question is, can you figure out that this is a JPEG from like reading part of the Huffman-coded area of the JPEG, or from reading the footer, or from reading the color table? These are different parts inside the JPEG. And you can, but it's work. So this is called the file fragment classification problem. It's very easy with some file types, like HTML, because you might find an HTML tag. We came up with a technique for doing it with MPEGs and really with any frame-based multimedia format. It turns out you can identify the individual frame headers inside the byte stream, and they always have an offset of the next frame header. And so by threading together multiple frame headers, you can make a decision as to whether this is inside a multimedia file or not. Now, this is the area where there's been 10 years of research, and most people have done it with machine learning using bigram analysis. And you can't compare anybody's work to anybody else because everybody's done it with their own data sets. Rather than working in the machine learning area, we decided to just write hand-tuned discriminators for each file type and see how far we could get with that. So there are artifacts in JPEG files, and it turns out that the JPEG format says if there's an FF, it has to be followed by a 00. And so we didn't know the parameters for tuning this, but what we did was we did a grid search on the supercomputer, and we built all of these different kinds of hand-built classifiers with tunable parameters, and then we did a large grid search to find the appropriate parameters. And here's an example of the JPEG detector with the particular parameters that we discovered to use. With the blue sectors are the ones that are detecting as JPEG. And then these are other sections. This one meets our high entropy test, but it doesn't meet our FF00 test. This one's mostly ASCII. Turns out that's the EXIF that is now in JPEGs. A lot of them are stored as XML. But as the JPEG gets bigger, the area that we identify as being JPEG increases. And with this 2 megabyte JPEG, we're getting the whole thing because we have a good detector. So we have detectors now for JPEG and MPEG and Huffman-coded data and distinct data. If you have a big database of multimedia, it turns out every sector in most multimedia files, JPEGs, MPEGs, are distinct on planet Earth. There's so much entropy in video that it's just not repeated. So if you could have a big database of the hash codes of every single sector in your entire collection of stolen documents, and then we read a sector and we hash that and it's a match, then you know that that sector really did come from that image. And in part, we can do this because file systems tend to align files always on the same byte boundaries. So we combine the random sampling and the sector discrimination, and we can actually accurately get the forensic contents of this iPod. And they match the contents as reported by iTunes. So that's very, very exciting. and so we don't have code that we're releasing on that yet, but it works. And what we're trying to do now is to build up more detectors. And we'll probably implement some of that n-gram stuff too, but we have some ideas on how to make it better. So I've been asked to finish by 12:30. It's 12:29 and 38 seconds. I'm not going to make it. Where do we go from here? So there's a lot of projects to pursue. We need a lot of algorithms. We need algorithms that work with different kinds of data, that work with different resolutions, with different orders of magnitude. You might have 12 million data objects on somebody's hard drive, and you want the tool not to fail when it gets a drive that's really interesting. We need to use machine learning techniques to automatically identify outliers and inconsistencies. One of the hallmarks that a system has been broken into is that there's some inconsistency. The one case where I actually testified in court, there were typos in a log file. Now, normally computers don't put typos in the log file, so we were able to use that as evidence that the log files had been tampered with prior to being printed. But we don't have software that can automatically find typos in log files, because log files were actually not created to be read by computers. They were created as debugging tools for the original programmers. And there's a lot of opportunity to use things like social network analysis or existing techniques for personal information management on this data. And a lot of the techniques that we develop will be useful for those fields as well. So my real challenges are to innovate, to actually get data, get tools, get techniques from the lab into the field. And to do that, we need to be able to address issues of scale. We never know how much data our users are going to have. There's a lot of attention to usability and to recovery. The tools have to be able to produce useful results even if they crash. We use high-performance computing to do testing, but our users won't have access to those techniques. And I'd like to use programming languages that are safe and high performance, but a lot of the underlying tools that we have are all written in C. And so there's just traditional software engineering problems. So the reason that I was able to come up here is I'm trying to get other people interested in this field. We desperately need people who have expertise in other areas to look at the computer forensics problems. It's of national importance. We have really hard problems, and we have bad guys, and the bad guys have more resources than we do now. The only advantage we have is we have more data. We have access to more data. Now, the people running the botnets, they may have more data too, but they don't. It's not going to help them protect themselves. Most of the work that's been done in computer forensics has been on data recovery and reverse engineering. And those are important problems, but we can't keep up by just doing reverse engineering because there are more people developing new file formats than there are people trying to crack them. So we're falling behind. And there are more people developing new file systems and new operating systems. We need to have techniques that are aware, that are able to do analysis in real time and make use of those results. So this is an interdisciplinary problem. We need work in systems and network engineering, machine learning, natural language processing. It's all there. And the problem is the people who are the real experts in this field, when they come to computer forensics, it's just too hard to work with the data. I had a guy from Wall Street, and he spent 6 months trying to figure out how to get the Windows registry into an XML format that didn't generate errors with his XML parser, but still was in a useful format. So there are so many opportunities to work with outside CS. Opportunities to engage policymakers and police and the defense bar. Most use of computer forensics now is to find evidence of guilt. There's practically nobody using this to find exculpatory evidence. Law enforcement doesn't look for that evidence, and the defense bar doesn't have the resources to do forensics because the examiners are just too expensive. Another question, like I mentioned earlier, the cell phone problem, right? Well, what if every cell phone sold in the United States was required by law to have a data extraction protocol if you had possession of the cell phone? Right, so this would be like CALIA for cell phones. Well, why do that? Well, it could be a pro-consumer thing to allow consumers to get data out of their cell phones, but it would also be useful for law enforcement. That's an interesting public policy debate that nobody's even having right now, and yet every police department in the United States is frustrated by the difficulty of working with cell phones. So I'm at the end of my talk, and 4 minutes over. Have to take out slides. Any questions? So it depends on your operating system. But the thing that depends upon your operating system is what happens to the rest of the sectors. Some operating systems blank them. Some operating systems leave them filled with the previous data that was on the drive. The question that you asked is, if you read a sector and you see the 0 filled from the back, what information does that tell you about the bytes there at the beginning? And that's a really interesting question that I've never thought about. So it could be that you have a small file, and it could be that you have the end of an existing file. And there are some file formats, it's all details. It's all details in forensics. There are some file formats like the zip, which puts the central directory at the end of the file. And so you could use that to get information about what's stored in the zip file. But there are other file formats that don't. And so that would be a really interesting study to look for these sectors that are 0 filled from the back and to see if you could get power out of doing that and learn things in a faster manner that it makes it so you don't have to do analysis of the entire file. And I'd love to help you on that. I'm not aware of anybody who's done that. That's a really neat idea. Yes?
An active, aware adversary, because if they were active and aware, they would be just encrypting everything anyway, and the game would be over for you?
So that's an excellent question. There are people who just encrypt everything, and we don't, we have other ways for dealing with them. Increasingly, there are Linux distributions that create a small bootable volume and then have everything else encrypted. But that's not going to be the big problem for a while. Our adversaries, like I have a whole bunch of hard drives that are from cyber cafes in India and Pakistan. There's a lot of crime that goes down in cyber cafes. And we don't have tools that work well with cyber cafes because it's basically all residual information left over from browser caches and deleted files. Be really nice to be able to distinguish that one user from another user, create the usage profiles. The best that we can do now is with the tool that I have. The bulk extractor will actually, when it sees compressed data, it will decompress it. So we can extract all the email addresses that are on that cyber cafe hard drive. Cell phones, for the most part, do not encrypt their contents. We have the ability to extract the data from many kinds of cell phones. And we're running bulk extractor on the cell phones. But there's a lot of interest in figuring out how to reconstruct the data records in the cell phones themselves. Now, that's hard. And it's especially hard because we don't have the cooperation of the cell phone vendors. And it's hard because they change their data formats on a quick basis. For the most part, we don't have an active adversary. When we publish things like particular techniques, there may be a very small percentage of people who stop using those techniques. In this respect, our biggest adversary is the open source privacy community and Microsoft. The more privacy tools that are in the operating system, the more they're turned on by default, the more difficult it is for law enforcement. And that's a very, very interesting tension. The tension may go away with cloud computing, because with cloud computing, if we have access to the cloud, a lot of stuff in the cloud will not be stored encrypted. I don't know what the future holds. I know that we have at least 10, if not 20 years of good time ahead of us examining desktop and laptop systems. Yeah. So that's a really good question. There are very few publicly reported cases of bad guys using steganography. There is a commercial tool called Gargoyle, which detects known steganography. I have a really interesting PhD thesis, if I can just find the student, of analyzing file formats and then using the description of the file format to analyze exemplar files and to see if there are some files that have different distribution of implementation of that file format, like different use of magic numbers or different stuff in the unallocated area than other files. So there's a steganographic technique that was recently published, which is Microsoft doc files are basically fat file systems. They contain little file systems. And that means that they can be fragmented inside the data streams. And so you can store a 1 by having 2 blocks following each other in order and a 0 by having them in reverse order. So we have this ability to encode information in doc files. It'd be very interesting to have a technique that can discover that steganographic technique just by examining the spec and examining example documents. Unless we can get above the steganography game and actually approach it with that kind of insight, we're never going to catch up, because there's always going to be some other way of encoding secret information. And as long as the adversary keeps their steganography program hidden, we'll never know that it's there because we won't know to look for it. So I gave a talk in Ireland, and there was a master's student that came up, and he was coming up with a new steganographic technique, and he was going to publish it. It was his master's thesis. He was really excited. And I just said, please don't do that, because it's not socially useful to come up with new, well-engineered steganographic solutions, approaches for doing steganography. It's not hard to hide information in a way that existing tools won't find it. It's hard to come up with ways of finding information that's hidden without knowing that technique in advance. Yeah. I'm sorry? Well, I could certainly imagine that future. I've read about it in science fiction. I don't think it's likely. But it would be bad if we ended up into that future. It would give our adversaries tremendous advantages. And I think that there'd be a lot more use of detention on people who don't give up their keys. Yeah. Yes. It's remarkably easy to frame somebody. So we need more tools that look for inconsistencies automatically, because it's very hard to frame somebody perfectly. So the easiest way to frame somebody is to get their username and password and log in as them and do your crime. But then you have like the stolen account scenario. So you'd like to do for forensics, looking at their data stream and see if it's consistent with the person or not consistent.
Is there also a problem where when you're doing the illegal stuff, you might not be consistent yourself? Is it kind of looking at child porn?
Yes. Yeah.
So
the standard defense against child porn is somebody else did it. Like somebody else was using my computer, there was a bot. And so in those cases, we tend to look for, like the standard way to deal with that defense is if they burned it onto a CD and they wrote something on the label, like teen or preteen, then that's really good evidence of intent. For the most part, most people aren't being framed, which makes when the tool is used to frame people all that more powerful. Most digital documents aren't brought into court, but the ones that are used as evidence, therefore, have a much higher likelihood of being fraudulently constructed. And so when I teach forensics, I stress again and again that they need to identify not just that this is sensitive data, but they need to really figure out who is responsible for it. And it's a problem, and it's a problem that needs more rigorous attention. And our problem in this field right now is there just aren't enough researchers. There's a lot of money available for doing research. There's a lot of compelling problems. We don't know how often people have been framed. I'm sure that there are court cases out there that we could collect and start to build a story about those cases and be able to understand the indicators of when somebody is actually being framed. But that work hasn't been done. Yeah.
I'm trying to figure out what the right question is to get my onions on the table here. So basically taking the posture that the government and law enforcement are the good guys, and we need to have more of these kinds of research, more of these kinds of tools, so that the bad guys who are child pornographers and various other people like that can be caught. So my question, I guess, if you could put a concrete edge to it, is are the governments of totalitarian regimes aware of your research, and are they using it against various forms of freedom fighters?
That's an excellent question. There's some other questions which are, what sort of auditing do we have built into the tools so that they won't be misused by our government? And the question is, how do you frame that trade-off between civil liberties in the United States and protection against surveillance? We have many cases in recent history of the government engaged in illegal surveillance. It has happened within recent memory. And And those are important questions. And the totalitarian issue is perhaps the easiest one to deal with. Because for the most part, our government, well, I can't even say that anymore. That we don't use torture.
To discourage a graduate student in Ireland from publishing a new steganography technique, you might as well tell everybody who's involved in anti-circumvention tool building to stop it, because because then people would be able to hide what they're doing, which is bad for society.
So that's a good point. There's many privacy protecting technologies that require work. But one of my dissatisfactions with the graduate student in Ireland is that it's just too easy to come up with new steganographic techniques. So I didn't think it was it was particularly intellectually relevant pursuit. And I didn't see the social value in putting out a new steganography technique. But this is a real problem. It is a problem that our techniques are used by people in countries that we don't like. It's a problem that our network security techniques are used by criminal organizations to secure their networks. It's a problem that all the research that we've done in phishing has been used by the people engaged in phishing to do better phishing attacks. So this is a general problem in the field of security, academic computer security, and that when we publish, the adversary has access to what we do.
Well, not just our adversaries, but they don't think, the people I'm worried about are not people who think of themselves.
Right, but our government does view those governments as adversaries, because we officially are in favor of promoting democracy. So when people use our forensic techniques, yeah. And it's a real problem, and I just don't have a good solution for you. But it's not a problem unique to this area. Yes. And I hope your laptop's encrypted. And I think you should. No, I think that, well, I think that only people who are not engaged in crime should encrypt their laptops. And I would encourage you to encrypt your laptop. And if we can push on that, you'll probably have a key recovery technique, or you'll probably have the data on your laptop stored elsewhere. So if you were a university employee who was following university rules and using a managed system and engaged in fraud against the university would probably have a way for getting access to your unencrypted data. And if you were a superior criminal and you defeated those mechanisms, then at some point what you'll be doing is you'll be denying access to the university of your data. And I think that that's the future. But we do have a window now to be able to exploit this data. And I think we have an obligation to exploit it if possible, because their lives will be saved by exploiting it. And at some point in the future, if all the systems are encrypted, then we'll have to do something else in computer forensics. then what we'll probably do is we'll probably break into the systems and run the software on them when it has access to the key. Yes?
So I wonder following up on Harry's question, for development of forensic tools, to what extent is the sort of unease about helping only law enforcement and governments that maybe not necessarily behaving the way we want them to, would it be resolved by your bullet up there about engaging with the defense bar? Meaning, is it conceivable that this becomes as useful for defense as law enforcement, or are the resources so asymmetric here that forensics will always be?
So the only time I've testified in court was for the defense. And one of the problems that we have is that forensic experts that work for prosecution are barred from working for the defense, because if they work for the defense, nobody else on the prosecution will ever hire them again. And the prosecutions have more money. So this is one of the reasons why I think it's important to develop automated open source tools so that they're available for everybody to use. And all these tools that find sensitive information, they can also be used as privacy screening tools to see what your leakage profile is. If, that's a justification. But it's true, right? So the problem is now that a lot of people are carrying around sensitive information and they don't even know that it's there. Like my PhD work, people were throwing out hard drives and didn't know that there was sensitive information on them. And so we reported that, and we tried to get, I spent a lot of time trying to get Microsoft to fix the format command. And they fixed it in Vista. In Vista, partially because of my efforts, when you format a hard drive, it actually overwrites every sector of the hard drive. In Windows 7, it does that. But the delete command still leaves deleted files. Now, I'm still trying to get Microsoft to fix the delete command. And with solid-state devices, it probably will be fixed. Because with SSDs, when you write to a flash memory cell, it's actually a two-part process where the page gets erased and then it gets written. If you can proactively erase pages and hold them in reserve, the write operations are faster. And so the ATA protocol has something called the trim command, where it will go out, you can say these sectors are not being used by the operating system anymore, and the underlying firmware in the SSDs will reallocate things and wipe the pages. And that's going to be built into Windows and Mac OS. So the ability to access deleted files is going to go away within the next 3 years on people running modern hardware with SSDs. I think that's a good thing, because it's probably good for privacy. It is good for privacy. But it's interesting to compare that with the idea of the fully encrypted world in which the only information that's on my hard drive, nobody else can access it. What we'll probably see in that case is more people being held in administrative detention until they give up their keys. Yeah.
Relative to the sector sampling, are there any white list programs like random data rather than all zero?
There are. Yes. And so we will pick that up as an entire drive that was encrypted, because you can't distinguish between encrypted data and random data. Yes?
So TrueCrypt has two different definitions if you want one. So you can give up one key without giving up the other key.
Yeah, the problem with that is that everybody, the adversary knows that, right? So then they beat you until you give out the second key. And if you don't,
It's not really very useful.
no, it's a really bad idea. So because TrueCrypt has this deniable encryption layer, if you don't use it, you're asking to be tortured. Right.
Okay, so people seem to be
Okay, well, thank you all for coming. I really appreciate it.